For today's notes, we will finish up Standard 13. This is part 4, using trigonometry to solve application problems, and you will need in-class 57 to follow along. We will be using our same three relationships, the sine, cosine, and tangent equations and ratios, to help us solve situations. The difference is that we are going to be able to read a description to label a diagram that's already been started for us, or later on we'll actually create the diagram for ourselves, and then we will decide whether we're solving for a side or solving for an angle, and what is the best fit between sine, cosine, and tangent. All right, as we get started, the thing that you need to realize is that all of these situations can at least be loosely modeled with some kind of right triangle. So when we talk about a boy that's letting out 30 feet of string on a kite, we assume that that kite is up in the air. That's confirmed by the next sentence where it says the angle of elevation, which remember is from a horizontal up, is 27 degrees. And then when we are asking you how high is the kite, that's actually this vertical distance to the ground that makes a right angle, sometimes called the altitude. So that's what we're solving for in this particular problem. As I read that first sentence, a young boy lets out 30 feet of string on his kite. That means that the hypotenuse of this triangle, or that string that connects the boy to the kite, kind of awkward that it's connected to his foot, but that's okay, is 30 feet long. And so now what we have is a right triangle where we know an angle that we can use as our reference angle, and we know a side, and we're looking to solve for another side. That gives us a way that we can use, hopefully, either sine, cosine, or tangent, depending on what our labels are actually related to. So if that's our reference angle, x would be the side on the opposite side of the triangle. 30 is across from the 90, so that means it's the hypotenuse. When we have the opposite and the hypotenuse available, that means we can write a sine equation. So we're going to have sine of the reference angle 27 equal to the ratio of the opposite side x over the hypotenuse 30. These are going to be solved the same way that they were in the previous day's worth of notes. So when we're looking to find that x in the numerator, right now it's divided by 30, so we need to multiply by 30, which means that we're headed to the calculator with a multiplication problem. 30 sine 27 should tell us what our x is equal to. Make sure you're in degree mode, remember. Always double check that. And then 30 times sine of 27 is going to give us a decimal like always. I don't see it in the directions for this page, but it should say to round to 2 decimal places like we're used to. So we're going to look at that third decimal place. Since it's a 9, it tells us to round that up. So x would be equal to 13.62. Let's be a little bit more careful with that. I'm rounding. So x is approximately equal to 13.62, and the units for this problem are feet. So that kite is approximately 13.62 feet up in the air. Moving on to scenario B here. It says we've got a 20-foot ladder that's leaning against a wall. So the ladder itself is 20 feet. It's leaning against a wall so that it can reach a window 18 feet off the ground. So that 18 feet is that vertical altitude perpendicular distance off the ground. So that's this side of the triangle. And then they want to know what's the angle of elevation from the base of the ladder to the wall. Base is bottom, so from there to the wall would be an angle of elevation up, which means that is what we're solving for. You could put an x there, or if you remember, we use theta as our mystery angle. So if we're at that reference angle, even though it's a mystery, we know the side on the opposite, the other side of the triangle for opposite. We still know the hypotenuse, so this is still a sine equation, but it's a sine equation where we don't know the reference angle, and we can fill in the entire ratio of opposite over hypotenuse instead. Remember, when we're solving for an angle, we're going to need to slide that sine inverse in on both sides of the equation, which will leave just the theta on its own on the left, but then sine inverse of the ratio 18/20 on the right. To do that in our calculator, we're going to need the second button before we click sine to bring up that inverse sine command, and then 18/20 gets filled in to give us 64.158. That 8 tells me to round that 5 up, so 64.16 will be degrees because we were solving for an angle this time instead of a distance. Onward we go to part C. To support a young tree, Jack attaches a guy wire, that's this thing right here, from the ground to the tree. The wire is attached to the tree right there, 4 feet above the ground. So that means this vertical distance that makes our right angle is 4 feet. If the angle formed between the wire and the tree, all right, that's not an angle of elevation or depression, so let's read it carefully. The angle formed between the wire and the tree. The wire and the tree come together here at the top, which is why they haven't called it an angle of elevation or depression, because it's not connected to a horizontal. It's connected to a vertical. So that's 70 degrees, and they want to know what is the length of the wire. So in this picture, the wire is that diagonal side of the triangle, so that's going to be what we label with our variable. If we use that 70-degree angle as our reference angle, we don't know the side over on the opposite side of the shape, so we don't have opposite, but we do know the hypotenuse across from the 90, and we do have the side next to our reference angle, which is the adjacent. Those two force us to use a cosine equation this time. So cosine of 70, the reference angle, equals the adjacent over the hypotenuse. Now remember, there's 2 ways you can deal with an x in the bottom of a fraction. Either make it into a proportion and cross multiply, or just multiply both sides by x to get that out of the denominator. That results in an equation that can't quite go into the calculator yet because the x is not isolated, but x is multiplied by something. So we're going to come back in and divide both sides by the cosine of 70, so that now we have x equal to 4 over, or 4 divided by, the cosine of 70. That will go to our calculator. We don't need inverse cosine because we're not solving for an angle. So just 4 divided by cosine of 70 gives me 11.695. That 5 tells me to round that 9 up, so it's like we're rounding 69 up to 70. So it should be 11.70 if we round to 2 decimal places. So x is approximately 11.70. The units for this problem were feet. I'm just now noticing up here in my previous example, I forgot my approximately equal to there. We did round that angle, so it's better to use that approximate equal sign rather than the equals equals. All right, one more on this page where we've got a picture partially set up for us. We've got a helicopter directly over a landing pad. Billy is 110 feet from the landing pad, so here's Billy. The distance between him and the landing pad would be down here along the ground. So that side is going to be 110 feet. Our right angle is going to be right here. If Billy is 110 feet from the landing pad and the helicopter is 80 feet high in the air, so that's giving us this vertical distance, 80 feet high, the altitude, what is the angle of depression from the helicopter to Billy? All right, angle of depression is supposed to be from a horizontal down. So there's actually not an angle of depression in this picture. So what I need to do is I need to put out a horizontal line of sight from the helicopter towards Billy, which means this angle right here is actually what I'm solving for. Now there are 2 ways to deal with this. You could either duplicate this triangle up top like this and focus on using that blue triangle. The left side would match the right side, so we could fill in 80 feet. The top would match the bottom. This would be 110 feet because what we've really created here is a rectangle. And then you could solve for your x by thinking about this top triangle. Or the other option, if you want to continue to use this bottom triangle that I have outlined in brown, is we need to think about how horizontals are parallel to each other, which means this angle of depression is an alternate interior angle with this angle of elevation down here at the bottom. So those are going to be equal to each other. Now I used x here because that's most of your instinct, but you could also put theta since it's a mystery angle. Most people use this bottom triangle, so that's the one that I'm going to focus on. If that's our reference angle, then 80 is the opposite side and 110 is the adjacent. We don't know the hypotenuse this time, so we should be writing ourselves a tangent equation to solve this problem. Tangent would be related to the x reference angle, or theta if you like to use that, and then we would have opposite of 80 over adjacent, which is 110. Since we're solving for an angle, we need to remove this tangent from the equation using tangent inverse. So x will equal tangent inverse of 80 over 110. We head to the calculator. Second tangent pulls up that inverse tangent, and 80 over 110 is our ratio. So we've got 36.027. That 7 rounds up that 2. So our angle, x or theta, is approximately 36.03 degrees. All right, that takes care of the 4 examples on the front. Go ahead and flip the page over to the back. We have 4 more examples to do together, but we don't have pictures started for us. So we're going to have to visualize these and set up our triangles on our own. All right, scenario E is about a man that's casting a shadow. Shadows are along the ground, so we know that that shadow is going to be 3 feet long. We need to pick a side of this for the man to be standing at, so I'm going to put him over here on this side, which means in order for his shadow to be back this direction, that means that the sun is kind of over here, shining down and hitting the guy, and then the shadow is behind him. Now it says if the sun's rays strike the ground at a 62-degree angle. So that means we're visualizing these rays coming down and hitting the ground at a 62-degree angle. So that's going to happen at the end of the shadow. That's where the sun's rays will hit the ground. So this angle right here is going to be the one they're talking about that's 62 degrees. They're asking us for the height of the man. So that would be this vertical side of the triangle. Okay, so our little setup looks like that. If that's our reference angle, 62 degrees, we've got the opposite side, x, and then the adjacent side, 3. We don't have the hypotenuse because it would be weird to measure sun's rays in the air. We can't really do that. So this is going to be a tangent equation. Tangent of the reference angle, 62, equals the opposite over the adjacent. We are going to be able to isolate that x by multiplying both sides by 3. So 3 times tangent 62 is what I'm headed to the calculator to use to find that x. 3 tangent 62 is equal to 5.642. That 2 tells me to leave that 4 alone. So this man is 5.64 feet tall, approximately. So he's a little bit more than 5.5 feet tall. All right, our next scenario is about somebody that's in a lighthouse tower. Now, I'm not a good artist, so I'm not going to actually draw a lighthouse, but I'm going to pretend that the lighthouse is right here. He's up top, so he's up here. If you want to draw a little stick figure, feel free. Okay. It says that he's 30 feet off the ground, so that's going to tell us about his vertical distance from the ground. I'm going to draw in the ground. He spots a ship at sea that's 200 feet from the base of the tower. So there's some kind of ship out here, that's my boat, that's 200 feet away from the base of the tower. So 200 feet, somewhere along here the ground is turned into water, but that's not really important for us to know. We're going to connect these together to make that triangle happen, and then the question is asking us to find the angle of depression from the man to the ship. So if we're at the man, we need a horizontal, and then angle of depression would be from there down. So I'm going to need to take this whole triangle and flip it up top, or remember that horizontals are parallel, so that angle of depression from the man to the ship is really the same as the angle of elevation from the ship to the man. If that's my reference angle, I know the opposite side and the adjacent side. So we're going to write a tangent equation. Tangent of theta equals the ratio of opposite over adjacent. And to solve for that reference angle, we're going to need to use tangent inverse. So theta will equal tangent inverse of 30 over 200. Make sure you actually type in second tangent to get that tangent inverse up, and then 30 over 200 for our ratio. 8.530, so no rounding up, just 8.53. So theta, or the angle, is approximately equal to 8.53 degrees. You might think that's a really small angle. Well, that makes sense. He's 30 feet in the air, but he has to look 200 feet away. So that's going to be a really long, skinny triangle in real life with a really small angle here and a much larger angle there. All right, 2 to go. A 20-meter tall telephone pole. So telephone poles are usually straight up in the air, 20 meters tall. Cast a shadow 18 meters long. Shadows are along the ground. So 18 meters down here. What is the angle of elevation from the end of the shadow to the top of the pole? Elevation is from a horizontal up, so they're asking me to find that angle right there. Very similar to the last problem. We've got the side opposite still and the side adjacent. So just like in the last problem, we're still writing a tangent equation, but this time the ratio is 20 over 18. We're still going to use tangent inverse to get that theta by itself on the left. And so tangent inverse of 20 over 18 should tell me what that angle of elevation is equal to. 48.012. That 2 means we don't need to round it up, so 48.01 is my approximate measure for that angle of elevation in degrees. All right, last one. We've got another kite flying scenario. So we're going to have somebody who's flying a kite up in the air. Again, my artistic skills are not great, but there's the kite. The kite's on a string that's 130 meters long, so I'm going to go ahead and label that. Determine the height of the kite. So we're looking for that vertical distance again. I think this means height of the kite if the string creates a 37-degree angle of elevation with the ground. So that string and the ground from a horizontal up is an angle of elevation, so that works out just fine. We're looking for the side opposite, and we know the hypotenuse. So that will tell us to use sine this time of the reference angle 37, and that will be equal to the ratio of opposite over hypotenuse. Since we're solving for a side, we don't need inverse sine. We just need to get that x by itself. So 130 times the sine of 37 should tell us what x is equal to. 130 times sine of 37 equals 78.235. And that 5 tells me to round up, so 78.24. Units for this problem are meters, and that's going to be approximately the height of the kite in the air. All right, that's it for today. Thanks for watching. That finishes out our standard 13 notes, so we'll see you back in class to start the review process.